All right, guys, so we're going to be looking at an introduction to Chapter 8, Energy Production. I've decided to go on to this unit first just because this unit is a lot more informational. There's not a lot of labs and hands-on things to do, and so I think it's probably a good unit for us to do while we are out for now. And then hopefully by the time we get back together, we'll be able to do some more interesting things and be able to spend more time on the hands-on activities and labs and other things. So let's go straight into it. The first thing I want to talk about is the first law of thermodynamics. All right. Now, this has several pieces to it, but basically the first law of thermodynamics says the energy of a system remains constant unless one of two things happen. First, work can be done on or by the system, right? If work is done on the system, that means something is putting energy into your system. Or if your system does work, then it requires or uses energy to do that work. And so therefore, the energy of the system will change if work is being done on or by the system. Heat can also be transferred, right? And we've talked about heat as being the energy that's being transferred from one object to another. So if heat is transferred to the system, obviously it has more energy. Or if heat transfers out of the system, it can have less energy. Now, of course, that heat can be in different forms. It can turn into the kinetic energy of the molecules, right? There's various ways that can show up. But what we want to focus on is that unless one of these two things happens, then the energy of a system should remain the same. All right. Here's a convention that we use. We use this convention because IB uses this convention. Work is positive when the system does work. Okay, your first law of thermodynamics will have an equation, and in that equation, work is considered positive if the system is doing the work. All right. Heat is positive when energy is transferred into the system. Okay, now this may change depending on your convention, right? This in IB will always use this one. However, when you go to university, it is possible that they may change one or both of these. All right. So I don't want you to get to university and be like, but Mr. Bywater said he lied to me. No, I'm not lying to you. I am giving you the convention that is used by IB, but it is just that. It's just a convention. So we will always consider work to be positive when work is done by the system. I know that my university textbook actually did the opposite there. It said work is positive when work is done on the system because that meant that energy was coming in. But that's not what we're going to use. Work is positive when work is done by the system, and heat is positive when energy is transferred into the system. Okay? So consider the human body, right? Here's you. All right, if you're offended by that, you can pretend that it's me. All right, so here's me. Yep, I'm looking good. So when you eat food, okay, like pizza. I've eaten lots of pizza. My kids like pizza. I've eaten lots of pizza over the last few days, a couple of weeks. So I'm eating my pizza here. What happens to the energy in that pizza? Why am I eating that pizza? Well, the pizza has different elements in it, different atoms in it. Depending on the bonds, it has a certain amount of energy. That we call that chemical potential, right? That chemical potential goes into my body, and it then creates body heat, right? Now, that body heat is an example of that energy being put into the system. So that would be considered a positive, right? Because now my body is able to create more heat, more energy than it used to. Okay, so my internal energy will increase when I put food into it. Okay, now if I don't exercise very much, then that energy is turned into fat, right? And so unfortunately right now, yes, this is not really me. I am more like this. So right now I'm fat. Okay, and the reason why I'm fat now is because I'm not using that energy that's coming in. So that potential energy that's being put into my body that should be heat energy is not being used up, and so therefore it's being turned into another type of internal energy. It's being turned into fat. Okay, so that's internal energy. Okay, that's staying inside of me. It's not being used, right? Now, the other thing that can happen is if I decide to go out and work out so that I can go back to my normal, beautiful self, then that means that I am doing work on the outside, right? I will do work that then allows some of that internal energy to go away. All right, now this can be demonstrated by a formula. Okay, the amount of heat is equal to the internal energy plus the amount of work. Now remember, heat is positive when energy comes in. So the energy coming in either goes to internal energy, because that energy coming in turns into fat, or it goes to work. I use that energy that heat energy then to do something, right? To run or jump or go hiking, whatever. All right. This often is rewritten in a slightly different way. Okay, but this is the same thing, right? The total internal energy is equal to the heat, right? Because heat going in means that I have an increase of internal energy, minus the work, right? Because if I am doing work, then I should be losing internal energy, all right? And positive work is defined as me doing work, or the object doing work. All right, so that is the first law of thermodynamics, which basically is just the conservation of energy. All right, let's move on. The second law of thermodynamics is a little bit more complex, so we're not going to take a whole lot of time on it. However, you need to have the basic idea. It can be stated in many, many, many different ways, okay, but it can be seen in many different ways as well. So here's a couple of the ways that you can see it. Okay, one way in which second law of thermodynamics is described is that energy cannot go from a body with low temperature to one with high temperature without doing work on the system, right? So if I have this pot here, which is very hot, the water inside is boiling, and then I have my nice cool hand, which is about to touch it. Yes, I'm amazing at drawing. The energy will not go from my hand into the hot pot, right? What happens when you touch the hot pot? The energy goes from the hot pot into your hand, which is why your hand gets burned, because it gets too much energy and it burns the material inside your hand. Okay, what it's saying is exactly that heat will not go from a cold to a hot unless you have some way of forcing that to happen. But to force that to happen, you need a force, and therefore you must do work. Okay, so that's one explanation of the second law of thermodynamics. Another way to look at it is you can't take energy from a hot place and turn it completely into work. And this seems like something slightly different, but it makes sense in the long run. Just understand, if I have something that has a certain temperature, I cannot take all of that heat and turn it into work. The problem is, if I take heat out of here, so say this is really, really hot, as I take heat out of there, the heat goes somewhere else, right, into the environment, which means that the temperature of the environment then increases. If the temperature of the environment increases, then I'm never going to be able to get this guy down to 0, because this guy will only go down until it's the same as the environment around it, right? So it's impossible to take all the energy from here and turn it into work unless you do work on it, which then is inefficient and we don't want to do. Okay, so that is another way of talking about second law of thermodynamics. And another way is, some of you in chemistry may have heard this word, entropy. Entropy is basically disorder. Okay, disorder will always increase. Okay, basically that means that concentrated areas of anything will tend to less order. They will spread out. Okay, this should make sense. I mean, if you have a hot pot or a hot cup of hot chocolate sitting in your room, I do hot chocolate because I don't drink coffee, so here's my hot chocolate. It's sitting there. What happens? I have a high concentration of energy here, and what happens to the energy? It leaves, right? The energy leaves, it warms up the room around it, and the cup cools off. That is a concentration of heat. What happens if you take a beaker of water, right? So I got a beaker of water here, and then I take some red food coloring and I drip it in. Okay, what's going to happen to that red food coloring? Does it stay as a drop there? No, it doesn't, right? The food coloring begins to spread out and disseminate because, why does it happen? Because the molecules in the water have temperature. If they have temperature, temperature is proportional to kinetic energy. So those water molecules are all moving around. So as they move around, they hit those red molecules and cause it to move around. But that is the natural way of things, that this concentrated red then spreads out throughout all of the water. Okay, try it at home. If you got some food coloring, take just a cup. Don't mix it up. Just take a cup of water and put 1 drop of food coloring in it. And you'll see that over time, it is going to spread out. Okay? Really, really neat stuff. Anytime you have a concentrated anything, it will tend to spread out. If you put a bunch of charges together, right? We haven't talked about electricity yet, but I mean, you know how it is. If you put 2 positive charges together, what happens? They spread out, right? They push away from each other. They have a repulsion, right? Well, what if I have a whole bunch of positives here? What's going to happen? Well, entropy says that they are going to tend towards disorder. They're very orderly. They're very nice right there, but that's not going to stay. They are going to spread out because they repulse from it. There's always a reason why, but entropy, disorder, will always increase. Things aren't going to get more organized as time passes. Okay? These are all explanations of the second law of thermodynamics, and they're all linked into each other. But I think as long as you have these ideas, you're probably okay to move on to the next idea.